Okay. In the last lecture, we finished vector space and we now have subspace. Okay, we finished the first section in this chapter, which is about vector space, and we now have subspace. We say a subspace of W of a vector space V. Here it says W is called a subspace of V. We say W is a subspace of V if it satisfies these conditions. If W satisfies these conditions, we have two conditions on W to be a subspace of V. If we take any two vectors from W, so the sum of them must be in W. That means it must close under addition. This is one of the conditions in which W to be a subspace of V. And the second condition is, let K be any real number and U is any vector in W. Ku must be in W. Ku must be in W. So the vectors in W must have these two properties. One, the sum of any of the vectors in W must be in W. And if we multiply a scalar by any vector in W, must be in W. So if W satisfies these two conditions, means W is a subspace of the vector space V. Okay? Look at this example. Here it says V is the vector space R2. Is the vector space R2. So R2 is AB, where A and B belongs to R. This is R2. This is these. This is all the points on this form, A and B. Okay, A and B are any real numbers. Okay, now it says W is A and 0. Look, the second term, the second element is fixed, which is 0. It says W is called a subspace of R2. Why? So W must satisfy both conditions. That means if we take any two members of W, the sum of them must be in W. That means we must get the same form. We must get a value and 0. The sum of any two vectors in W must be on this form, value and 0. Okay? And if we multiply a scalar by any vector of W, must be on the same form, value and 0. Let's check if we could do it or not. Here, we take two vectors in W. The vectors in W are on this form. The first entry is A, is a constant, and the second is 0. We take these two entries, these two vectors. These are vectors in W. As you see, both have the same form, A0, B0, C0, Z0. All of them are in the same form. The first entry is a constant, and the second is 0. The sum of these two vectors is A plus B and 0. As you see, this vector is still on the same form of vectors in B. The first entry is a constant, A plus B is still a constant. And the second is 0. So it is in W. The sum of them is in W. That means if we take any two vectors in W, the sum of them is still in W. The second condition is if we multiply a scalar, let's say K, C, any scalar, if we multiply it by any vector in W, we must get the same form of the vectors in W. Look, if this is a vector in W, if we multiply it by a constant, let's say we get CA and 0. Is on the same form as you have in W? Yes. So it is still in W. That means both conditions are satisfied. That means W is a vector, is a subspace of R2. Here V is R2. Okay? So W is a subspace of V. Here you have another example. It says let W to be this form. The vectors in W are in this form. Constant, 1. The last element must be 1 always. Okay? The first two elements could be any real value. Could be any real value. Now, look, let's take two vectors in W. We say let U to be a vector in W, which is A1, B1, 1. And V be any vector, be any other vector in W. It is, let's say, A2, B2, 1. Look, if we take any vector in W, must be on the same form as it's defined there. Let's find the sum of them. We say the vectors in W are all in the form that the first two elements are constants and the last one must be 1. Okay? It must not be any other value. Look, U plus V is what? It's A1 plus A2. It's okay. It's a constant. Then B1 plus B2. 1 plus 1 is 2. Look, the last element changed. It becomes 2. Is it in W or not? It's not in W, because in W we say the last element must be 1. It must be on this form. Okay? Okay, the first one is still a constant. It's okay. The second is still a constant. But the last one becomes 2. So it's not on this form. In this form, we say the first and second must be constants, and the last must be 1. But here we got 2. That means this doesn't belong to W. That means W is not a subspace of V or R3. Okay? It's not a subspace of V. Okay? That's it. Here we have another example. It says let M 2 by 2, that means the set of all matrices, all 2 by 2 matrices. VM here, M2 by 2 is the vector space which is the set of all 2 by 2 matrices. With the vector space of 2 by 2 matrices. With the standard operations of addition and scalar multiplication, and let W be the subset of all 2 by 2 matrices which trace is 0. Look, W is the set of all those matrices in which the trace is 0. What's the trace? The trace is the sum of all elements in the diagonal. As you see, this is the diagonal in a 3 by 3 matrix. Let's say 1, 2, 3, 1, 1, 7, 2, 2, 7. The trace here is these elements. It's the sum of these elements. Okay? It's the sum of these elements. It just lets you know what's the trace. Okay? Then here W is defined by this type of matrices, 2 by 2 matrices, in which the trace is 0. That means the sum of elements on the diagonal, these two, is 0. The sum of these two is 0. Let's take an example for this. We say 2, 0, 7, -2. The sum of these two is 0. And also you can say 0, 2, 7, 0. It's also the sum of these two is 0. Then -1, 7, -7, 1. The sum of these two is 0. Minus 3, minus 5, 4, 3. It's also 0. As the set of all those matrices, we have infinitely many matrices on that form. We need to show that if it is a subspace of M2 by 2 or not. How to show that W is a subspace of M2 by 2 or not? We take any two members from W. We must show that the sum of them is still in W. The sum of them is still in W. And also, if we multiply any member in W by a scalar, we must get a member in W. Look, here we take two members. We let W1 and W2 be two members in W. Since these are in W, that means in this matrix, the sum of these two is 0. That means A1 plus B1 is 0. Because we have these conditions on the elements of W. We say the sum of these two is 0. As we took these two vectors from W, that means the sum of these two is 0, and the sum of these two is 0. A2 plus B2 is 0, because these both are from W. Okay? Now, let's find the sum of them. We must get a matrix. We must get a matrix in which the sum of these two elements is 0. The sum of those two elements is still 0. Okay? Let's check if the sum of these two matrices gives us a matrix on that form or not. Look, W1 plus W2 is the sum of these two matrices. Okay? It's A1, B1, C1, D1. That's W1. And this is W2. Okay? Now, the sum of these two matrices is the sum of all corresponding elements. That's it. Okay? We find the sum of these elements and we get the same size matrix. So we get a 2 by 2 matrix. This is an entry, this is an entry, this and this. We have these 4 entries. Now, if in this matrix the sum of these two elements is 0, means it's in W. That means it's in W. If the sum of these two elements is 0, let's check. We say A1 plus B1, then plus D1 plus D2. We say A1 plus A2 plus D1 plus D2. If this equals to 0, means the matrix that we go from the sum of those two matrices is in W. This equals to adding two numbers is commutative, so you can say it is A1 plus D1 plus A2 plus D2. But you already know that A1 plus B1 is 0, and A2 plus B, sorry, it's D. A2 plus D2 is still 0. So this equals to 0, and this equals to 0. That means 0 plus 0 plus 0, which is 0. Look, the sum of these two entries in this matrix is 0. Can you say it is in W or not? Yes, we can, because on the same form of the matrices in W. That's the first condition, yeah. If it wasn't 0, we say it doesn't in W. So W is not a vector space of. We say it's not a vector space, a subspace. We say W is not a subspace of M2 by 2. But if it satisfies all the conditions, both conditions, we say W is a subspace of M 2 by 2. Okay, that's the first condition. For the second condition, if we multiply any member in W by C, here in this matrix in W one that you took, the sum of these two, A1 plus D1 is 0. Okay, if we multiply it by C, we still get 0. We must get 0. Okay, we get this matrix as we multiply all elements by the scalar. And here, if the sum of these two is 0, CA1 plus CD1, this equals to, if we take C as the common, we get A1 plus D1, which is C times 0, because this equals to 0, so it is 0. It's on the form of the matrix in WS. That means it satisfies both conditions. Okay? As it satisfies both conditions, so you say W is a subspace of M2 by 2. Okay? So W is a subspace of M2 by 2. And here you have some 2 exercises. That's for yourself. So it's the end of this part of chapter 3. In part 2, we have here in this section, we talk about span, basis, and dimension. In the first section, we just talked about vector space. In vector space, we have 8 conditions. We talked about that. And in subspace, we have only 2 conditions. We say a subset of a vector is called a subspace for the vector if it satisfies those 2 conditions that we talked about today. If we take any 2 vectors from the subset, the sum of them to be in the subset, and also if we multiply any vector of the subset by a scalar, must be in the subset, so it becomes a subspace of the vector. Now we have span, basis, and dimension. Okay, here it's all depend on linearly independent and linear combination. Okay, in the previous chapter we talked about that, and it's based for these sections in chapter 3. Here for span of vector, we say let V be a vector space and S be a finite set of vectors V. Here S is a finite set, is a finite number of vectors in V. S is a finite number of vectors in V. We say the span of S denoted by span S. Here we denote it by this. Or span the vectors in S. The same S is those vectors. Is the set of this linear combination. Okay? Is C1 V1 plus C2 V2 up to Cn Vn. Okay? In other words, we say determine if every vector in V can be expressed as linear combination of vectors in S or not. If the vectors in V could be expressed in the linear combination of vectors in S, we say span S is a subspace of V. Okay? Here, in solving examples, it will be much clearer. We say the span of a single non-zero vector in Rn, yeah, if we have span V, which is the set of all scalar multipliers. If we have only a single vector, we just multiply it by C. Okay, this is V. This is V. If we multiply it by C, we get, let's say here. By negative C, it comes to here. It's like this. Okay. The span of two vectors is a plane. As you see, if we have v1 and v2. v1 and v2 are these two vectors. Okay, cv1 is up to here, cv2 is up to here. So the plane which is made by cv1 and cv2 is the sum of them. Look, that's it. We make this parallelogram. Okay, so this plane is the span of the vector if we have only two vectors in it. Okay, look, in examples, it's different from what we did above, actually. In this example, it says let S be the subset of the vector space R3 defined by this. It says show that span S, show that V is in span S. Okay, it says show that this vector is in span S. What do we do here? It's so easy. We just say C1 times, here we have only three vectors in S. C1, V1, let's say it's V1. This is V2 and V3. C1, V1 plus C2, V2 plus C3, V3 is equal to V, as you see, it's given as V. Now we find the values of C, C1, C2, and C3. Okay. If we could get values, different values, if we could get a value for each C1, C2, C3, means V is in span S. We can say V is in span S. Look, think about linear combination. In linear combinations, we said if a vector could be written as the linear combination of some vectors, what we did? We said, let's say, what we say, if we say this vector could be written as the linear combination of these three vectors. What we did here, we said CV1 plus CV2 plus CV3 for the vectors in S is equal to this vector. And then we try to find the values of C. If we could find values of C, and if we don't get some impossibilities, means it is the linear combination. So V is the linear combination of S. If it's satisfied, means V is in span S. It's the same. So what we do? Here, this is V1, this is V2, and this is V3, and this is V. Okay? That's what we write down above. This is V. It says, is this vector could be written as the linear combination of these, or is V in span of these three vectors or not? Okay, here it's asking about span. It says, is V is in span of these three vectors or not? What we do, we just try to show if V could be written as the linear combination of vectors in S or not. If we could, means it's in span S. If not, we say so. Okay, look, CV1 plus CV2 plus CV3, C3, V3, okay, is equal to V. Now, we write down the augmented matrix. If we multiply these by C1, these by C2, these by C3, and these are the elements of the right-hand side, we get this matrix, okay? This is the first column, this is the second column, and this is the third column, and it's the fourth, so it's the third one, not the. This is the third column, and it's the fourth one. Okay, we have these four columns. What do we do to find the values of C1, C2, C3? In the linear combination, we said we use a reduced row echelon form. Okay, we use Gauss elimination or Gauss-Jacobi or any other method. Okay, what we do from this element, we try to make these two to 0. Okay, and from this element, we try to make this to 0. That's it here. I think we solved many examples about this, about reduced solution form, so that's why I'm not gonna do it again, okay? From this element, we try to make these two to 0. As you see, we did it. And we change itself by 1. Then, for this, after doing this, we come to here. From this element, first we change it to 1, and we try to change these to 0. Or if you use Gauss elimination, just change this to 0. Look, we changed both to 0. Then we change this to 1, and we try change these two to 0. If you put a matrix like this, if you don't get a 0 row, okay, means it is in the linear combination of the members in S. So here, this is C3. C3 is -1. C2 is 1. And C1 is -2. As you see, we could get 3 values for C1, C2, and C3. Okay? And also, it's possible if one of them is 0. It's okay. Okay? If they are 0, it's okay also. Look, C1, C2, C3 are -2, 1, and -1 respectively. That means we say V is C1 times this plus C2 times this plus C3 times this. Okay? That's it. So you could write down V as the linear combination of vectors in S. That means we say it is in span S. So V is in span S. That's span. That's all about span. If you could write down as the linear combination, we say it's in span S. If not, we don't. Look at this example. In this example, it says determine whether these 3 vectors span R3 or not. We have given these 3 vectors. Okay, it says all these 3 vectors span R3 or not. What we do, we say C1 V1, C2 V2, C3 V3 is equal to, what are the elements in R3? We have 3 components. Okay, we name them X1, X2, X3. We don't write down 0 for all. Okay, it's not given. But you should know it's 3 tuples. The elements in R3 are 3 tuples. So you have this equals to X1, X2, X3. We now write down the augmented matrix. The augmented matrix in the first vector is this, the second is this, the third and the fourth. These are the vectors, I mean the columns in the augmented matrix. This is the augmented matrix. Now, from this one, we try to make these two to 0. And then from this one, we try to make this to 0. And if we don't get any impossibilities, means it's on the linear combination of those vectors. Look, here we get, this is 1 C3. Okay, so C3 is X3 minus X1 minus X2. Is it in R or not? If we have 3 elements in R, if we have 3 numbers, let's say 3 real numbers, the sum and subtract them, is still a real number or not? Yeah, of course, it's still a real number. That means it's still in R. And this is in R. This is in R. That means we get 3 values for C1, C2, C3. Okay? We get 3 values for C1, C2, C3. So what means? It means these 3 vectors span R3. These 3 vectors span R3. That's it. C1 is this, C2 is this, and C3 is this. If you give any value to C1, C2, C3, you get 3 values for. So if you give any value to X1, X2, X3, you get a value for C1, a value for C2, and a value for C3. That means we could write down these 3 vectors. So you could write down this vector in the linear combination of these 3 vectors. Okay, it means these 3 vectors span R3. That's, you even don't need to write down this. From here you can decide, as none of the rows is 0, so you don't get any impossibility. You can directly say that here this is the value of C3. If you put it here, you get the value of C2, and if we put the value of C2 and C3 here, we get the value of C1. That means we get values for C1, C2, C3. So it means we could write down R3 as the linear combination of those 3 vectors. It means those 3 vectors span R3. And here we have this. It's the same for R3. R3 is X, Y, Z. Let's say X1, X2, X3, or A, B, and C. And any variables you can use. X, Y, Z. Okay? Or X1, X2, X3. It's the same as the above. It says, is this show that this spans R3. Okay? And also this one the same. It says these 3 vectors span R3. So change to this form and work on it. We now have basis of a vector space. Basis of a vector space. We have 2 conditions for a vector to be a base for a vector space. Okay? We have 2 conditions on a set of vectors to be a base for a vector space. What are the conditions? First, it must span the vector. Okay? It must span the vector space. And then the vectors must linearly independent. Must linearly independent. We say we must get that. For example, here, if this is V1, V2, let's say it's V3. Okay, we have these 3 vectors. If we have these 3 vectors, we see these 3 vectors. Let's take 3 different vectors better. If we have, let's say 1, 2, 2, negative 2, 3, 0, 0, 4. To show this 3 vectors is a base for R3 or not, what we do? We must try 2 conditions. First, we say these vectors must span R3. Span R3. These 3 vectors must span R3. And also, we say these 3 vectors must be linearly independent. We talked about linearly independent in the previous chapter. Okay? In linear independent, we said if we have C1 times V1, plus C2 times V2 plus C3 times V3 if it equals to 0, 0, 0. We must get 0, C1 must be 0, C2 must be 0, C3 must be 0. That means we must get 3 values for C1, C2, C3, and all are 0. Okay? So in this case, we say V1, V2, if this is V1, this is V2, if this is V3. We say these 3 vectors are linear independent in this case. So these 3 vectors must satisfy these 2 conditions. Then we say these 3 vectors is a base for R3. Okay? Look at this example. Here, it says show that this set is the basis for R3. Okay? We need to show 2 things for B. Okay. First, we need to write down R3 as the linear combination of these 3 vectors. That means these 3 vectors must span R3. Must span R3. What are the vectors in R3? We pick any vector from R3. Okay? Let's take it generally. In R3, the vectors in R3 are X, Y, Z, or X1, X2, X3, or A, B, C. If they are variables, you are free to choose any of 3 variables. Okay? Let's take A, B, C. These are the vectors of R3. Okay? A, B, and C are any real number. To show that these 3 vectors span R3, we must write down this vector as the linear combination of these 3 vectors. Okay? You must do that. Now, we say C, this is V1, this is V2, as you have 3 vectors in it. This is V3. You say CV1 plus CV2 plus CV3 is equal to what? Equal to the vector in R3. Okay, if the vector in the space is not given, you should know in R3 is in this form. In R2 is in this form. In R4 is in this form. We have 4 tuples. Okay? But it says base for R3. So you should know that the vectors in R3 are on this form. Now we write down the augmented matrix. This is the first column, second column, third, and fourth column of the augmented matrix. Now we solve it. We try the reduced row echelon form. From this one, we try to make these two to 0. And from this one, you can change these two to 0. And from this one, the above ones to 0. As you see, we get this. We get this matrix. Okay? Now, we say C3 is minus A plus B. C2 is this. And C1 is this. As you see, we got 3 values for C1, C2, C3. That means we could write down vector ABC as the linear combination of these. If you couldn't get values for C1, C2, C3, that means if you get some impossibilities here, if this equals to 0. If this equals to 0. Okay? In this case, we don't get any value for C3. That means, and also 0 doesn't equal to minus 8 plus. Okay? So here, in that case, we say it's not the linear combination of the vectors V1, V2, V3. We say If we get some impossibilities like that, if this is 0, we say it's not here. The vectors doesn't span R3, okay? But in this case, as we get C1, C2, C3, as you get three different, I mean, three values for C1, C2, C3, that means APC could be written as the linear combination of the three vectors. That means the vectors V1, V2, V3 spans R3. Thus, the three vectors spans R3, or span B is R3. It's the first condition. We have another condition to show that those three vectors are basis for R3 or not. What we do, we need to show that these three vectors are linearly independent. To show that some vectors are linearly independent, we say C1 times the first vector plus C2 times the second vector plus C3 times the third vector must be 0, 0, 0. In this case, we must get 0 for all C's, okay? We must get 0 for all C. C1 must be 0, C2 must be 0, and C3 must be 0. And then we say these three vectors are linearly independent. If at least one of them is not 0, we say okay. We say if we don't get values, if we don't get 0 for C1, C2, C3, we say those three vectors are linearly dependent. But if we get 0 for all C1, C2, C3, means those three vectors are linearly independent. Okay, let's solve it. Here we get this. So C3 is 0, C2 is 0, C1 is 0. Look, I'm not doing this, how to get this matrix from this. Here we use reduced row echelon form. We talked about this type of examples in many examples before. Okay, so C1, C2, and C3 are all 0. That means those three vectors are linearly independent. In another way, we can show that if we have three vectors or two vectors are linearly independent or not. Look, if you get a square matrix from these three vectors, so you get what? Remove these. We get a square matrix. A square matrix is a matrix in which have the same number of rows and columns. So it's 3 by 3. Find the determinant of this matrix. Find the determinant of this matrix. If it's not 0, means they are linearly independent. If it doesn't 0, the determinant of this matrix, if not 0, look, that's it. That's how to find the determinant. It's -1. It doesn't equal to 0. That means those three vectors are linearly independent. You don't need to do this one. You don't need to do step 2 here. You can just find the determinant, and if it equals to 0, we say they are linearly dependent. But if not, if it doesn't equal to 0, if it's any value, negative, positive, any value, we say the vectors are linearly independent. Look, these three vectors, in B, these three vectors satisfy two conditions. We say these three vectors spans R3, and also these three vectors are linearly independent. So they satisfy both conditions of basis. That means these three vectors are basis for R3. They are basis for R3 because they satisfy both conditions. So B is a basis for R3. B is the three vectors. Okay. Here you have one example. It says determine whether these three matrices are basis for M22 or not. Are basis for M22 or not. M22 means a matrix of 2 by 2. So we generally take a member from M22. We say, let's this be a member of M22. So this is the form of members in M22. Okay? We say these three matrices must satisfy two conditions to be base for M22. Okay? First, let's say it's V1, this is V2, and this is V3. We say C1 V1 plus C2 V2 plus we say it equals to A. Now we must get values for C1, C2, and C3. Okay, we use the dissociation form to get the values of C1, C2, and C3 here. And then this is the first condition. And in the second condition, here, if C1 view what we talked about. Okay. We said if C1 V1 plus C2 V2 plus C3 V3 equals, this is 0. It's a 0 vector. In this vector, we have 3 elements. Okay. If in this system, we get C1 to be C2 to be C3, which is 0. If we get 0, that means these three vectors are linearly independent. So it's the second condition. If it satisfies these two conditions, if A could be written as the linear transformations of V1, V2, V3, and also if V1, V2, V3 are linearly independent, that means these three vectors are basis for M22. Okay, here we take A by ourselves, it's not given. But you should know in M22, it's a 2 by 2 matrix. So the elements of a 2 by 2 matrix is in that form. Okay, look, for this example, what we do, we say C1 times the first element of B, C2 times the second, C3 times the third, equals to what? Equals to A. This is for linear combination, okay? For linear combination. We write down the augmented matrix. We say C1 Zarbi is C1 times 1 plus C2 times -1 plus C3 times 0 is equal to A. That's it. Here we get 1, -1, 0 is A. Then C1 times 3, C2 times 2, C3 times 1 is equal to B. That means 3, 2, 1, B. This is our second row. For the third row is 2, 1, 0, C. For the fourth row is 1, 0, negative 4D. That's it. We have this augmented matrix. It's the system. Now, what we do? We use a reduced resolution form. If we could get values for C1, C2, C3, means we could write down this matrix as the linear combination of these. If not, we say it's not. Look here. We get 0, 0, C3 is this one. Is it possible to 0 equals to that? Okay, it's not. So here we get some impossibilities. 0 equals to a value. So it's impossible. 0 is a value. It's impossible. That means here we say we don't get values for C1, C2, C3. So those three matrices, these three matrices, we say these three matrices are not span M22. They are not span M22. Okay, because we couldn't write down A as the linear combination of these. So these three doesn't span M22. That means it doesn't satisfy one of the conditions. So it's not base. Okay? If it is base, it must satisfy both conditions. It must span M22. And also, these three matrices must be linearly independent. Must be linearly independent. Okay? But here, the first condition, it doesn't satisfy. It's not satisfied. So we say these three matrices are not, look, doesn't span M22. Therefore, B is not a basis of M22. It's not a basis of M22. That's all. If it doesn't satisfy one of the conditions, we say it's not a basis. Look, for dimensions, we say zero vector space, zero vector space has dimension 0. But for n, dimension of Rn, dimension means, yeah, we say how many elements do you have in it? Okay, dimension of Rn is n, because in each vector of Rn we have n entries. Okay, dimension of R3 is 3. Okay, here we have 3 bases. Look, dimension of this matrix Mn, a matrix of M by N, is M times N. It's M times N. And the standard basis of a 2 by 2 matrix, look, we have 4 elements in the basis. These are bases for M22. It's the standard base. Look, the standard base for R3 is this. As you see, it's 1 here, and 1. This is the standard base. But for the matrix of 2 by 2, I mean a 2 by 2 matrix, it is dimension is 2 times 2. 2 times 2 is 4. That means you must have 4 elements, 4 vectors in the standard base. Okay, it's 1, 1, 1, 1. Okay, we have 4 elements in the in any 2 by 2 matrix: A, B, C, D. Okay, for each element in the base, if this to be 1, others are 0. If this to be 1, others are 0. If this to be 1, others are. It's like that. Okay, so this is the standard base of a 2 by 2 matrix. For polynomials, the dimension is the highest degree plus 1. Let's say let f of x to be 3x squared minus 2x plus 2. Okay? What's the degree of this polynomial? It's 2, the highest degree. So what's the dimension? As you see, we have 3 terms. We have a constant term. That means we have one extra. I mean, the dimension is always the degree plus 1. Okay, so the dimension of Pn is n plus 1. So dimension here, dimension for polynomials, as we said, here the dimension of this polynomial is 3, because it's the highest degree plus 1. It's the degree of the polynomial plus 1. For example, here, for polynomial of degree n, Pn means a polynomial of degree n. Its dimension is n plus 1. We always add 1 for the degree of the polynomial. Here, as you see, we have n terms, 1, x squared up to x to the power n. Dimension of a solution space. Here, it says determine a basis and the dimension of the solution space of the homogeneous system. When it says homogeneous system, means the right-hand side is 0. Okay? And it says determine a basis. So we need to first find the base. Okay? We need to first find the base. And then the dimension of the solution. So dimension of the base. Okay? Dimension of the base. So for dimension of a base or the solution, we just look at the number of vectors in the solution. For example, if the base to be, let's say, 3 vectors. So its dimension is 3, because you have 3 elements in it. You have 3 vectors in it. Okay? What if B to be only 1 vector? Its dimension is 1. It depends on the number of vectors in the base. For finding the basis for this system, what we do, we first write down the augmented matrix for the system. The augmented matrix is this. Here, 2, 2, negative 3, 0, 0. That's the first row. The second, third, fourth. We have 4 rows. That's it. Okay? This is the augmented matrix. Then, we apply reduced row echelon form. We apply reduced row echelon form on this matrix to get this. From this, we try to change this to 0, and from this, we try to change this to 0, and from this, we try to change this to 0, and this, and so on. So, okay? We get this matrix. Okay? In that matrix, we say x1, x3, x4, x5 are leading variables. But here, look, from this reduced echelon form, what we get? This is negative 2. X, what's the x? It's x5. Is 0. So what's x5? Is 0. And we use this here to get x4. Say minus 3x4 plus 0x5 is 0. This is 0. So minus 3x4 is 0. So x4 is 0. x4 is 0 also. And if we replace x4 by 0, x5 by 0, we get x3 is 0. That means x4, x3, x5 are all 0, as you see here. How about x1 and x2? x1 and x2. x1 is leading theorem, and x2 is free variable. We studied this before. We just replaced the free variables by a value, by a parameter. We let x2 to be a. How about x1? How to get x1? We replace. Yeah, we have this equation 2x1 plus 2x2 minus 3x3 plus 0x4 plus 1x5 is 0. x5 is 0, x4 is 0, x3 is 0. So these three terms become 0. What else do we have? x2 is a. That means 2x1 plus 2a is 0. How about x1? x1 is minus a. x1 is minus a. That means the base, the only base that we get is the values of these variables. So the base is x1, x2, x3, x4, x5, which equals to a is negative, x is negative a. X1, x2 is a, x3 is 0, x4 is 0, x5 is 0. We have only this vector. Okay, that's. And here you can take a as the common, and we get this vector. So this vector as the solution actually. Okay, so v1 is the basis for the system. Is the basis for the system. And what's the dimension of the base? How many vectors do you have in the base? We have only v1. We have only v1. So S is v1. As you have only one vector in it, that means the dimension is 1. The dimension of the solution is 1, and the solution is the base. Okay, the solution is the base. And it's the end of this section. So let's take a break for 10 minutes. Okay. Okay. In part 3 of chapter 3, we have coordinates and change of bases. Here, we just talk about two concepts: coordinates and change of bases. Here, for coordinates, it's the values of C in linear combination. That's all. You just need to find the values of C, and the values of C are going to be coordinates. Okay? It's so easy. Here, we say, let B be a vector, be this space, V1, V2, up to Vn. Be an ordered basis for the vector V, vector space V. B is basis for V. And in B, we have n vectors, V1, V2, up to Vn. And let V be a vector in little v is a vector in capital V. And let C1, C2, up to Cn be unique scalars such that V could be written as the linear combination of V1 up to Vn. If you could write down any vector of the vector space by the linear combinations of the base, we say these values C1, C2 up to Cn, these values are called coordinates. Okay, the values of C, and as you find to show that the vectors in the base are linear combinations of any vector in V. In that process, we find the values of C. So those values of C are called coordinates. Okay. of V relative to B. These are called coordinates of V relative to B, and it's written in this form. V relative to B. Okay, so the coordinates of V relative to B is written in this form. This means coordinates of V relative to B. Now, look at this example. In this example, it says, let V to be R2 and B be the ordered basis. This is B. This is B. This is the base. It says, find the coordinates of vector V relative to B. This is B. What we do? We need to write down V as the linear combination of vectors in B. How many vectors do we have in B? We have two vectors. This is a vector and this is a vector. We have two vectors in B. So V is C1 V1 plus C2 V2. V is given. V1 and V2 are also given. What are unknown? Only C1 and C2. We can find them. It's easy. So V is 1, 5 is equal to C1 times V1 is 1, 1 plus C2 times V2 is -1 and 1. We write down the augmented matrix. It is 1, 1, 1, 5, 1, sorry, 1, -1 and 1. We write down these two first and this, okay? And then 1, 1, 5. This is our augmented matrix. We solve this for finding the values of C1 and C2. For finding the values of C1 and C2. Here, we use the reduced solution form to get the values of C1 and C2. And you get that 2C2 is 4. So C2 is 2. And you replace here. C1 minus C2 is 1. If C2 to be 2, so C1 is 3. We have these two values for C. Look, C2 is 2, C1 is 3. These two values are the coordinates. They are the coordinates of V relative to B, relative to the base. So we found the values of C1 and C2. C1 is 3, C2 is 2. This is the coordinate. This is the coordinate of V, vector V, was given. Relative to B. That's all. What we do, we just write down V as the linear combination of B, of the vectors in B. We find the values of C1, C2. Okay, the values of C1 and C2 are the coordinates of V relative to B. That's all. Here we have another example. It says, okay. Here we have another example. In this example, it says, let W be the subspace of all symmetric matrices in the vector space M22. Okay, so here W is a subspace of M22. And B is this set of vectors. We have 3 vectors in B. We have 3 vectors in B. We have this is V1, this is V2, and this is V3. It says find the coordinates of V relative to B. It says find the coordinates of V relative to B. B is given. B is the base. What we do, we just need to write down V as the linear combination of B. We say C1 times this matrix plus C2 times this matrix plus C3 times this matrix. It must equal to 2, 3, 3, 5. Okay, let's see. We get this. This is C1 times the first matrix in the base plus C2 times the second matrix in the base plus C3 times the third matrix in the base is equal to V. Now, what are the values of C1, C2, C3 to equal to this matrix? You can use, you can write down the augmented matrix and using Gauss-Roy form, and you also, it's easy here for this matrix to decide. This is here, you have only this element in this location. We have no, okay? So what C1 should be to get 2? C1 should be 2. Okay? سيكن ليرة لم لوكيشنه لشويها معنا تنها ليرة معنا أما الصفر كواتا سي شنبي الضربية كيف كم بوي كيف كاتا شي 2 سي بشنبي so C1 is 2 and then at this location these two are 0. We don't get any value from these two. We just get it from here. But here is 3. So we must get 3 by multiplying C2 with 1. So what's C2? C2 should be 3. And then for this one, it's the same. It's 3. How about this location? At this location, we don't get any values here, and then we just get it from here. C3 times 1 must be 5. So this C3 is 5. These are the values of C1, C2, C3. So these values, 2, 3, 5, is the coordinate of V relative to B. That's all. You just need to find these values of C1, C2, C3. Look, it's easy for this matrix to find the values of C1, C2, C3 in this way. But if you couldn't, what should you do? You need to write down the augmented matrix and solve it, okay? And find the values. I mean, use reduced row echelon form to get the values of C1, C2, C3. Okay? That's it. Now, VB, the coordinate of V relative to B is 2, 3, 5. That's all about coordinates. Okay? So for coordinates, we just need to find the values of C, C1, C2, C3, up to how many C's do you have? In the linear combination. That's all. Look, everything here depends on reduced row echelon form. After reduced row echelon form, it's important to know that what is linear combination, what is linearly dependent and linearly independent. You need these two also. As you see, all what we talked about today are about linear independent and dependent, and also linear combination. We didn't talk about anything else except that. So these all concepts depend on those. Okay? Then we have change of basis. Okay? In change of basis, it's just the explanation. It's not important. here, it's important to know these two rules. Only this rule. So VB is the coordinate of V relative to B. It is the coordinate of V relative to B. And here, VB dash, we need to find VB dash also. VB dash is the coordinate of V relative to B dash. If you have two bases, we change the base. Okay, we change the base. Now, we set equals to this. We now see what is this and what is this, how to get these two. Okay, now we have an example. If we just use these rules, okay, we just use these rules. First, we use this, and then we use this. Okay, here it's 5 to 6 slides, just explanation. I think it's not need, it doesn't need. Here we have an example. It says let V to be R2. So our vector space is the space of R2. Is the space of R2. B is these two vectors. In B, we have these two vectors. And B dash as these two vectors. It says find the transition matrix from B to B dash. So we need to find the transition matrix. We will find it. It's easy. And also, it says let V, the coordinates of V relative to B, to be this. We have given the coordinates of V relative to B. It says find the relative of V relative to B dash. What's about this? Here, we need to find two things. First, the transition matrix, then coordinates of V relative to B dash. Okay? Let's find them. We just used the above two rules for that. Look, it says find the transition matrix from B to B dash. It's different to say from B dash to B. Okay? It says from B to B dash. What we do? In B dash, we write down B dash as we write down each vector here as the linear combination of B dash. What we do, we say, let's say C1, 2, -1, plus C2, -1, 1 is equal to what? To the first vector. 1, 1. Then, again, for this vector, we do the same. We use C1, C2, and let's use D1, D2. D1 times 2, -1, plus D2 times -1 and 1 is equal to 1 and -1. That's it. Look, we write down this as the linear we write down each of these vectors. First, this one as the linear combination of these two, and also this one as the linear combination of these two. Again, okay? We write down the same, but the right-hand side is going to be changed. In the first one, it's 1 and 1. It's the first vector. In the second one is the second. This is, if it says, find the transition matrix from B to B dash. That means we need to write down the vectors in B as the linear combination of vectors in B dash. Okay? But if it says from B dash to B, we do it from here to there. Okay? Now, from these two, from this one and this one, What we get? We get values for C1, C2, and D1, D2. We get these four values. We get these four values. So C1 is 2, C2 is 3, D1 is 0, D2 is -1. That's it. Okay. Now, the coordinate of V1 and V2 are in V. They are in V. Okay. We say V1, the coordinate of V1, these are, okay, V1 and V2. The coordinates of V1 is the values of C1 and C2, which are 2 and 3. Okay. The coordinates of B2 are the values of D1 and D2. Look what we did. From when we equal this to this one, we get two values, which are C1 and C2. Okay, so these two C1 and C2 are coordinates for this vector. Okay, when we equal to this, the values of constants that you get here are the coordinates of this vector. So this is V1, this is V2. That means V1 and V2, I mean their coordinates relative to B dash are these two. So the transition matrix is V1, V2 as 2, 3, 1, -1. Okay? We say the transition matrix is the values of constants that you get in both cases. C1, C2, which is the first column, and D1, D2 is the second column. As you see, in these two cases, we get these values for C, these values for these, okay? And we get the transition matrix. The first column could be obtained from the values of C, and the second column are the values of D, okay? So this is the transition matrix. It's how to find the transition matrix, okay? It's easy. Just writing down these two linear combinations and find the values of constants. Write down the values of constants in a matrix, you'll get the transition matrix. Okay, that's it. Then it says, let VB equals 2 and -2. Find VB dash. Here it says the coordinates of V relative to B is this. So what's the coordinates of V relative to B dash? We need to find it for B dash. Look here, we use this rule. We just use this rule. It's just the multiplication of transition matrix with the coordinates of V relative to B. Coordinates of V relative to B is given. Okay, it must be given in the example. Now, what we do, and we also found the transition matrix. This is the transition matrix. In the first step, we found the transition matrix, and the coordinates of V relative to B is given. We just multiply these two to get the coordinates of V relative to B dash. That's it. This is just multiplication of these two. But be careful. You need to multiply the transition matrix by the coordinate. Don't multiply the coordinate by the transition matrix. Okay? You must multiply the transition matrix by the coordinates. We just multiply these to get this. And that's it. So it's 6 and 11. This is the required. That's just some extra things. Okay. Here, I said just find the coordinates of V relative to B dash. We found it. بله نه هسه رسته کش تا نمیده دقیق باشه بله بانگنگ هيك example من مالي هيك رسته ولا باشه. We have this example. It's the second example about the same topic about transition matrix and coordinates. Here, it says let B to be E1, E2, the standard ordered basis for R2. You should know that. You should know that B is. What's the standard base in R2? In R2, we have, for R2, we have X, Y. So what's the base for this? It is here, it's E1 and E2. It's given E1 and E2. It's 1, 0, 0, 1. Okay? It's 1, 0, 0, 1. This is the standard base for R2. You should know this. For R3, standard base in R3, the standard base is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the standard base for R3. But for R2, it is the above. Here, our example is about R2. This is B. And also B dash is given. Okay? B dash is also given. It says, find the transition matrix from B to B dash. It's the same as the previous example. What we do, we say, as it says from B to B dash, what we do, we say C times this, C1 times this, plus C2 times this equals to the first one. Okay? Then we get another linear combination. D1 times this, D1 times this equals to the second. From these two linear combinations, we get values for D1, D2, C1, C2. As you see, that's it. And we get the values of C1 is a negative a half, C2 is a half, D1 is a half, D2 is a half. Okay, so C1 is negative a half, and C2, D1, D2 are all a half. Okay, so the transition matrix is C1, C2, D1, D2. Okay, C1 is minus a half, and all the others are a half. That's it. This is the transition matrix. Now, we have the transition matrix, and we need to find the coordinates of V, relative to B dash. We say this equals to the transition matrix times V is given times V times of. We say multiplying by the coordinates of V relative to V. But V is given here. The coordinate is not given. V is given. V itself is given. How to find the coordinate of V? We say to find the coordinate of any vector. We just write down the members of the base, the linear combination of the base equal to the vector. We say C1 times this plus C2 times this equals V. And find C1 and C2, you will get the result. That's it. It's 3 and 4. As you have the standard base and you get the same. This equals V B. The same, it's the same because it's in terms of B. Okay. Here we just multiply. This is the transition matrix. This is the transition matrix, and this is the coordinate of V relative to B. We just multiply these two matrices, we get this. So this is the coordinate of V relative to B dash. That's it. That's the coordinate of V relative to B dash. And that's it. And it's the end of this section also. Let's take a break for 10 minutes. But before we do that, let me take the attendance. In this chapter, we talk about row and column vectors, and also we talk about rank basis of matrices. Okay. Here we have a row and column vectors. For any matrix, in a matrix, to find the row vectors and column vectors, we say for the row vector, it is the list of all rows of the matrix. Okay. For example, here in matrix A is an M by N matrix. To find the row vectors are the list of all vectors. This is the first vector, A11, A12, up to A1N. Then, this is the second vector. That's it. Then up to, this is the last vector. Let's take an example. So here in the next slide, you have some examples. You don't need to take it. For the column vectors, we say it is the first vector. This is the second, up to the last. So the list of all columns is called the column vectors, and the list of all rows called the row vectors. Okay, these are the column vectors. Here we have an example. We have given this matrix. To find the row vectors and column vectors, what we do for the row vectors are, what are the rows? The rows in matrix A are this and this. So you take each as a vector. It is 2, 1, 0. And 3, -1, 4. Sorry. This is the row vectors. Okay. This is R1 and this is R2. We have these two row vectors. So the row vectors are R1 is this and R2 is this. We have these two vectors. These are the row vectors. So what are the column vectors? For the column vectors, we say the first column is R1. R1 is 2 and 3. The second column is R2, 1 and -1. And the last column is R3, 0 and 4. That's it. These are column vectors, and the above ones are row vectors. That's how to find a row vector and column vector of a matrix. All rows, the list of all rows are row vectors, and the list of all columns are the column vectors. We now have row space, column space, and null space. You should know what's row space, what's column space and what's null space. Okay. We let A to be an m by n matrix. Here we work on a matrix for each of them. We work on a matrix for each of them. We say row space of matrix A, row space of matrix A, it is subspace of Rn spanned by the row vectors of A. So it means here it is all the subsets of Rn, all the vectors in Rn in which spanned by the rows of the matrix. Okay, spanned by the rows of the matrix. And for the column, it is the subspace of Rm, which is spanned by columns of the matrix. And for null space, we say the solution space of the homogeneous system of this equation, we just equal the matrix to 0. I mean 0 column vector. And then we solve it. Then we solve it. For the values of x in which the matrix is 0, for the values of x in which the matrix is 0, for those values are called null space. Those values are, so it's the solution. Null space is the solution for the homogeneous system. It's the solution for the homogeneous system. We'll take an example about each of these. Look, here, for the row space, we have two rows, C1 times this, and C2 times this. We just find the sum of them. Okay? We say XT, X transpose is C1 times the first row plus C2 times the second row. As we said, as it's the set of all vectors in Rn, which could be written as the linear combination of rows in A. As you see, this is a vector. This is a vector which is written by the linear combination of these two vectors. So X transpose is C1 times 1, C1 times 5, C1 times 3. Okay, and here we have C2 times 2, C2 times 6, C2 times 2. Then C1 plus 2C2, okay, C1 plus 2C2. And then C1 multiplying by 5 is 5C1. And C2 multiplying by 6 is 6C2. It is 5C2 plus. So it's 5C1 plus 6C2. That's it. Then for the last one, we just multiply this C1 to this bracket and C2 to this bracket. And then add these two vectors. It's easy to add those two vectors. First component with first component, second component with second, and third with third. And we get this vector. Here C1 and C2 are in R. Okay? So this is called row space. This is called row space of matrix A. It's for a matrix. Row space and column space are for a matrix, for a given matrix. So this is the row space of matrix A. Then to find the column space, what we do, we say C1 times this plus C2 times this and plus C3 times this. We have 3 C's here. In the previous one, in the rows, as you have 2 rows, you have 2 C, but here we have 3 C. Look, X is C1 times this transpose. Because it's column, we need to change to a row. If we write down in a row, we need to give a transpose to become this. Look, the transpose of any vector, let's say if you have 2 and 1, its transpose is 2 and 1. It becomes a column vector. The transpose of a row vector is a column vector. And also, transpose of a column vector is a row vector. Here, we just take transpose for these, or C1 times this, C2 times this, C3 times this. Now we introduce C to the brackets. And then we add all first components together. And then all second components together. We get C1 plus 5C2 plus 3C3. And 2C1 plus 6C2 plus 2C3, or transpose. This is called column space of A. This is column space of A. If we write down as the linear combination of the columns, so it's column space. But if you write down as the linear combination of rows, we say it is row space of A, and that's it is definition of row space and column space. And here we have an example about null space. For null space is the solution for the system. Is the solution for the system if all are equal to 0. Look, here you have this. For this system, we equal it to 0. So here, this is x1, x2, x3. Let me write down the system here. It is x1 plus 5x2 plus 3x3. And the second is 2x1 plus 6x2 plus 2x3. We equal these to 0, and then we write down the augmented matrix, and also we solve it to find the values of x1, x2, and x3. Look, if we write down the augmented matrix for this system is this. That's it. Now we solve this system by using a reduced Roshan form. From this one, we can make this to 0, and we get this matrix. And we cannot change anything else here. We cannot change anything else. Now, here we get minus 4x2 minus 4x3 equals 0. Okay? And so we can say x2 is minus x3, is it? We move it to the other side, dividing both sides by 4. We get x2 is minus x3. Look, in this case, we need to write down all the variables in terms of one variable. Okay? Look, we have x3. So the solution here, it's x3, x2, x1. This is the solution. We need to write down x1 as a function of x3. Okay? x2 as a function of x3. Look, we found x2. What's x2? x2 is minus x3. Now, from here, we have x1 plus 5x2 plus 3x3 is equal to 0. Here it's x3. We need to replace x2 by negative x3 because we already found that x2 is minus x3. We replace this by minus x3. What it becomes? Here we get x1, we get minus 5x3 plus 3x3 is minus 2x3, is it? It is minus 2x3 equals 0. So what's x1? x1 is 2x3. Now we change x1 to 2x3. Okay? This is the solution. This is the solution. Okay? Now, we say the null space is this. You can write down in this form or in this form. Okay? If we take x3 as the common here, what we get? x3, here we have 2, a negative 1, and 1. And you get this vector. So the null space is the set of solutions. What's the set of solution? Is 2x3 minus x3 and x3. This is the solution for the system, for the homogeneous system. When we say homogeneous, means the right hand side of all equations are 0. Let's check in. تنها لرا ساوي شكان صفر داني شكار يكن كشكار ما كن لفكاني اكسو اكسيكو اكسو اكسيو معنا ابنا شي null space ابنا null space باشا. So the set of solutions is gonna be the null space. So this is the null space. Okay, it's enough for today.